talking to a variety of experts in the area, there seems to be quite a tremendous potential for such savings. Actually, it is projected that by pursuing a fundamental research program on the demand side, we might actually save as much as 4 quads, so 4 quadrillions of BTUs of energy by 2030. Here is a comparison of what this looks like on the scale of other energy sources. Nuclear energy is here, and coal, you could actually cut off this much of the coal-produced energy. All other renewables are down here, and so on and so forth. Since buildings actually account for 48% of carbon emissions, such a program would actually allow you to actually start decreasing the CO2 emissions quite substantially by the year 2030. So here on campus, we have an initiative that has been rolled out just at this particular meeting called the Energy Efficiency Institute, whose director is Professor John Bowers in electrical engineering. And the mission of UCSB's Energy Efficiency Institute is essentially on the demand side. So while there is quite a bit of research going on the supply side with new and renewable fuels, on the demand side you have quite a bit of space to save, and that's linked to the graph that I've shown you on the previous slide. The strategic technologies that are being pursued within this context and featured in this conference are lighting and displays and energy-efficient electronics and networks, energy conversion, transmission and storage, transportation materials, and then systems and controls integration. And this particular session is mostly about systems and controls integration. In the session, we are going to have a talk on dynamical systems perspective in the flow perspective, control perspective, and an external perspective on how this all fits within the context of national needs. So this is all, in some sense, about dynamics and systems and uncertainty. While you might have individual components in the building being designed very well, and indeed, companies that do air conditioning, the companies that do HVAC, heating, and so on and so forth have been producing these components for a long time, and they are optimized individually. It is very often true that systems actually potentially could be fighting each other or not paying attention to the fact that external conditions change. In the hotels today, you're very often not allowed to open the windows for a variety of reasons, but one of them being that forced convection, the air supply to the room. The idea is that you don't want to lose that energy that is being utilized in pumping the air into the room for other reasons. I'm going to show you that that might not be exactly the right thing to do in a variety of contexts. In particular, a building, and this is actually a Marriott hotel in Atlanta, is a dynamic entity where occupants move through it, air moves through it, and flows up and down. And this particular hotel had a serious dynamics problem. That problem was that in the summer months, the amount of hot air that would come in from the bottom would pass up through this huge atrium, and the red that you're seeing on the top are temperatures that are above 90 degrees Fahrenheit that rendered that particular space in the hotel unusable. So they actually couldn't lease it out at all. The reason being that the temperatures were too hot, the cooling system was just not operating. It is the dynamics of the convection inside the building, the same kind of dynamics that drives large-scale convection in the atmosphere, that caused that particular phenomenon, and it was solved by our friends at United Technologies and Carrier by essentially providing an air curtain right in the middle that prevented the hot flow going from the bottom to the top. You could actually imagine putting a lot of sensors on the side and doing something optimal to it, like, for example, scheduling the airflow in stages from the bottom to the top to get an optimal distribution and even distribution of temperature as well. But that kind of a strategy that would be enabled by these kinds of sensors would need to vary depending on what kind of temperatures, external temperatures, you have to deal with. If there is a particular day on which the temperatures are down, then you might not need to use that sort of air curtain at all. Well, what prevents us from actually doing such things, let's call them quote-unquote smart things with systems and integration technology there? What prevents us typically is the fact that your meter at home looks something like this. right? This is a 1920 or 1930 technology, but you still have it, and each of our houses actually has one. Now, there's been a recent study by IBM that showed that if you use one of these smart readers that essentially show you how much energy you're spending, as a project by IBM, I think it was done in the Pacific Northwest, in Oregon. Just by looking at how much energy you're spending at a variety of places in your house, there are people that actually saved up to 40% over what was originally spent. So just getting more information, just getting smart information about what is going on in the building can actually get you somewhere if the occupants are aware of the problem. And today, with all the emphasis that we have on energy savings, certainly people are becoming more and more aware of it. But I'd like to offer you a bigger, grander picture of this. Imagine that same hotel 20 years from now, equipped with sensors that actually self-commissions. So it observes the external temperatures, so gets the weather data from the local weatherman, and then based on that, provides an optimal protocol that actually heats and cools the rooms individually, and of course, in negotiation with occupants as well. Of course, you're not going to be putting in the air that is 80 or 90 degrees Fahrenheit. If the occupant doesn't want that, you will actually have schedules to negotiate with the occupant as to what the comfortable situation is, but at the same time, the situation that actually saves maximum energy that you can save at any given time. So self-commissioning, self-adapting building is the vision that we'd like to propose and continue to describe in this set of talks. Now, in order to pursue such a vision, we need to do research on the side of what the brain of that building is going to look like. Your car has a brain of sorts, and the airplane has a brain of sorts, and your home doesn't, essentially. Your car adapts very well to what is going on the road, and it is going to turn on a four-wheel drive if you need it, and so on and so forth. And everything is actually going through either a central processing unit or a system of processing units inside the car, the embedded systems. In the building systems, typically, there is nothing like this so far. So that's certainly a need. So buildings are large, spatially distributed systems that need to be controlled. The unfortunate part for building design, but fortunate for research, is they are actually interconnected, multi-scale dynamical systems. You go from room neighborhood scale, in which you have to study various fluid flows that are going around, to building floor scale, to the whole building scale. And you have a variety of issues that you have to face there. Network sensor and control actually offer flexibility. You can time schedule either through a feed-forward type of routine or feedback type of routine with data assimilation, and provide energy, comfort, and security actually for the occupants. I mentioned security because, of course, some of the biggest problems in integration of important buildings that are occupied by, for example, government agencies, face today increased security issues. And if you imagine that you have a centralized air conditioning system and there is a contaminant inside the building, it has a potential to spread all over the building if you don't control it carefully. So while at the same time a centralized air conditioning system might provide you with some energy savings, at the other end of the other side of the coin, it's actually going to provide you with security threats, and that actually happened in the Senate a couple of years ago, if you remember the anthrax scare. So why UCSB? Why is UCSB a good place to perform research like this? Well, I'm trying to build a case that controls, systems, dynamics are essential for us to actually be able to reach, let's say, $80 billion in saving by year 2030 with the utilization of this interdisciplinary approach that actually combines the systems of a building, the sensors, networks, communications, controls, the natural ventilation, the HVAC, the indoor environment, and so on and so forth, into a system that actually smartly adapts to the environment. Is that really necessary? Well, you can actually take off-the-shelf technologies and achieve about 30 to 40% reduction right now. You can add to that with some of the tools that are going to be developed in the next couple of years, and you can save another maybe 20 to 30%. And then the potential here is to actually save 80 to 90% over 20 years from now. And that leads you to actually hundreds of billions of dollars in savings in a yearly energy bill that ends up being quite substantial. Here, and quite within the context of the Energy Efficiency Institute, we are starting a Center for Dynamics of Energy Efficiency and its applications. Integrated building systems is the topic that we're going to discuss today mostly, with fluid flow and thermal masses and sensors and so on. And here is a set of people that's actually engaged in research along these lines. If you produce too much energy in a building, you might need to store some of that energy in a variety of ways to actually to use it later. Energy storage is an important dynamical issue. Energy harvesting in micropower, there is actually a talk in this conference about it elsewhere as well, and some of our faculty are engaged in this. And then one of the topics that's becoming a topic of quite a bit of interest, although it's only consuming about 3% of the energy that I've been talking about, is that of data centers. Despite the fact that today this is at 3%, Google is going to make sure that tomorrow it is not, right? So these data centers have pretty severe problems with cooling and energy efficiency, and a number of us from both computer science here and mechanical engineering are engaged in research that would address that issue. There are a number of partnerships that we have had over the years and that we are actually developing right now in order to pursue the vision that I have just described. On the left, universities, UCSB here, UC Berkeley, and Professor Majumdar here is going to give a talk, who is at UC Berkeley is going to give the last talk in the session. We have had partnerships with Princeton, internationally with Warwick, with Caltech, Paderborn, Georgia Tech, and so on and so forth. And the idea is that here at the university, we are actually doing disruptive long-term basic research. But we are connected to institutions like United Technologies Research Center, which is a unit of United Technologies Corporation, that actually, as a business, one of their business units has Carrier. Carrier is the biggest producer of HVAC components in the world currently and has the biggest share of the market. So that loop between basic research and market that is a large-scale topic of this conference is actually enabled by this overlapping set of interactions. Recently, we had a set of meetings at the Lawrence Berkeley National Lab that I'll describe just briefly, and then Arun is going to talk about much more. Government agencies like DARPA are interested in supporting aspects of this research, and the purpose here is to drive market needs and problems to academia, but then, so this way, and then drive solutions back to market. Modeling for design is a topic that I'd like to stress out within the context of the technical structure of this. Why modeling? If you would like to design a large-scale building like Marriott from scratch, it might take you about 2 years to actually do all the thinking about how exactly to design it so that it saves energy. If you could reduce that time to, let's say, a month or two using modeling and design procedures, it would save a lot of money, obviously. Is this unprecedented in the engineering world? Certainly not. You all flew a Boeing 777, who is essentially designed in silico on the computer. So there is a lot of design and modeling, or there are a lot of design and modeling tools that are being used in automotive industry, in airline industry, but not many of them are actually being used, or there is not such an abundance of tools for the purpose of designing efficient buildings. And to summarize all of these, before I actually just briefly touch on a couple of research topics of interest, building is a multi-scale dynamical system with complex control mechanisms. Energy can be saved by using what we call smart controls. The issues that one needs to tackle in research are mechanics, fluid mechanics, control. Off-grid energy generation and harvesting requires analysis of dynamics of grid and off-grid coupling. I'm going to talk about it a little bit further. You'd like to trade off energy that is produced now for later usage. Methods of energy conversion and storage are necessary for flexible utilization of energy resources. We have a number of faculty in mechanical engineering engaged in such research. There is a collaboration that we started with computer science and external collaborations with Lawrence Berkeley Lab, United Technologies, and through the activities of Professor Walter Yuen at Hong Kong Polytechnic. And here are some images of these. So Here is a video that shows you what kind of technical problems can arise when you start thinking about designing smart buildings. Here is an air conditioning unit that was operating in a room in which the window was open, and as it was observed that the flow is going directly from the air conditioning unit to the window got closed. And you might think, well, that's an easy thing to do, put a sensor on the window and put a sensor on the air conditioning duct. And basically when the air conditioning sensor and the window sensor are both on, just close the window. Well, it might not be as simple as that, because the external air might actually be relatively cool by the time you're looking at this problem, and it might be, let's say, 60 degrees Fahrenheit outside, and you only need to provide a little bit of the air conditioning in order to actually provide a comfortable temperature for the occupants. So from that perspective, you'd need to measure the flow inside and put a sensor that would tell you what is optimal, what is indeed optimal in order to save the maximum amount of energy in that room. Very simple solutions, some of which are actually on the market right now, but it's interesting to do a simulation to see what the benefits are. So if you take a look at the room inside which we are actually pumping air, you're going to observe that if I actually just pump steady air inside that room, I'm going to, oops, let me actually repeat that. There we go. You see how there is some kind of a vertical motion being formed, and the particles of cold air, shown in blue, are not being distributed throughout the room. Now, if I just do something very simple, like oscillate the input, so in this case your louver would be actually moving back and forth here, you're seeing that the distribution of air, this doesn't work so well, the distribution of air after a while is actually very uniform inside this room. And in fact, if you measure that distribution and you try to estimate what kind of effect you have on energy efficiency, the blue and green curves down here are the ones that are obtained from various degrees of input. So you're turning this at various degrees angle. And the red and blue are the ones that are obtained by oscillating the flow. So you're actually getting about 40% saving just from that very, very simple mechanism. Now, what happens if you put a table in the room? Do you lose some robustness or not? Frédéric Giboux, a professor in mechanical engineering, has kindly provided these simulations. We have efficient methods to actually compute flow around such objects that also look quite pretty. But the point is that these are actually efficient, fast computations that actually provide us with the ability to efficiently design airflows the way we want them inside the room in a completely decentralized way. Okay, so far so good as far as the individual room is concerned, but buildings in general have more than an individual room. They have a whole system of floors and as I mentioned, systems. In fact, the whole building is a system of systems. You have, let's say, a boiler with heat recovery down here. You have electric load operation, real-time pricing externally to the building. You have a fuel cell, perhaps, for micropower generation here, the solar panels, the cooling tower, and so on, so forth. Well, how do you analyze that? I mean, is there a possibility to predict how a building is going to operate based on the external conditions? And the answer to that is actually today, the most advanced tool that you have is the one produced by Lawrence Berkeley National Lab that is called the Energy Plus. And Energy Plus, while a very useful tool and a tool that actually many designers use, is certainly not the kind of tool that would enable you to do the whole building simulation of, for example, the new New York Times building. You would need to work for quite a bit of time with a variety of parameters in order to actually make sure that the building operates as you would like it to. So we've developed a range of algorithms that actually enable the decomposition of this into smaller chunks that you can analyze very efficiently, design the subsystems, and the computation actually, for those of you that worry about how long is it going to take to compute, actually goes linearly with the number of components, which can provide you with the ability to scale time from, let's say, 2 years to 2 months or a month as far as the design time is concerned, which is a very substantial saving. On a 1 month turnaround, you can actually do something with it. So To finalize, let's move out, and thanks to Peter Allen for these great graphics. Let's move out from the individual building and look at the whole power grid. There is quite a bit of dynamics going on between individual buildings. Let's see if I get that again. Well, there is quite a bit of power that is going on between the buildings, and perhaps the power that is being generated at the building, if we get to the context of so-called zero-energy buildings, where the building is actually producing as much energy as it needs, or even more, that power could be actually redistributed between different buildings in the neighborhood by taking the energy from the grid, perhaps storing it, and then returning it either to the grid or to the buildings at an appropriate time. So dynamically scheduled, you again need smart sensors, smart controllers to actually distribute this in a correct way. Are there tools that will enable us to do this? Well, there is a current a program that we are doing with the partners from United Technologies that does enable us to go and look at the system of a variety of interconnected components where each of the components has a level of uncertainty associated with it. You can think of uncertainty as just basically a day-to-day variation of the climate. These tools actually enable us to take an uncertainty that has a very wide distribution, something like that, and then produce products whose distribution is within limits. And if, for those of you from industry, if this reminds you of the Six Sigma, it is. It's just that it is not a manufacturing Six Sigma where you're actually doing a static calculation of how many parts per million are you going to lose for bad manufacturing, but you're actually operating in an extremely uncertain environment where the weather is going to change on a hourly basis or maybe daily basis. Well, not in California, but in the rest of the country, presumably. And you're trying to maintain the quality of your product, in this particular case being the whole building system, within very tight bounds. Of course, to take an analogy from biology, that's what your body does all the time, but it has a very complicated processing system associated with it. This is why the timescale of having a smart building, or to use the analogy with Odyssey in Space 2001, a HAL of sorts in the building without the negative effects, hopefully, is probably within reach if you give it 10 to 20 years of developments. So in conclusions, energy savings in buildings is linked to efficient design of building systems. Perhaps the key message and the key output of the type of research that we are planning to pursue or are pursuing right now is the concept of so-called self-commissioning or smart buildings. So essentially you produce a building, it has a system of systems, it has a central processing unit, and based on the observations from the sensors, it actually self-commissions. It puts itself into an operating mode that is optimal for its occupants and optimal for its systems. What we need to do in order to get there is research on airflow mixing, sensing, and system-level modeling necessary to achieve these projected savings. Here at UCSB, we have a history of interdisciplinarity that is conducive to such research on building systems. And we have developed a set of partnerships with major national labs and commercial partners. And that's how much I had to say. Thank you.
Right, okay, so thank you very much, Igor, for a nice introduction. So I'm going to be talking about reduced order models for airflows in buildings, which is a specific method of trying to address this issue of designing more energy efficient buildings. I'll try to use this. As a quick outline, I want to start off with a bit of a historical perspective on designing buildings that, for example, are naturally cool, and perhaps make a brief case that this is a bit of a lost art. Then I'll go through some specific techniques for simplifying a system using the so-called proper orthogonal decomposition and Galerkin projection in order to come up with a reduced order model, which is easier to study and therefore hopefully will be usable for figuring out how to control airflows. I'll go through what I call an academic example, plain wet flow, just to illustrate how these techniques work and hopefully that they work. Then I'll have some comments on the industrial example of designing high-performance buildings, and then some thoughts looking forward. Okay, so probably for as long as buildings have been built, there's a common problem that buildings might be too hot on the inside for the comfort of the people. And historically, before air conditioners and so on were available, people put some thought into how do I design the building so that it naturally is cool. Some of the things that were done is to have barriers against the entry of heat. This could be as simple as sort of a shade that prevents sunlight from coming in or something like that. They also put massive masonry shells that absorb heat. You can think of these as thermal capacitors. They absorb the heat when there's a lot of heat coming in, and perhaps they radiate the heat later in the day when it becomes cool, or perhaps you have some sort of setup so that water flows by this and removes the heat away. Also using cool materials such as marble. There are certain materials that we know are just cool to the touch, and those can be used to help keep a building cool. An example where this was done quite effectively, now I've never been fortunate enough to visit the Taj Mahal, but I'm told by people who go there that the inside of the Taj Mahal is much cooler than you might expect it to be, given the outside temperature. For those of you who aren't familiar, the Taj Mahal was built in the 1600s as a mausoleum to the emperor's favorite wife, apparently, who died shortly after childbirth. Primarily, they're using this cool material concept that the air is flowing in through some sort of vents, and it passes over materials such as marble, which is cool, which manages to remove some of the heat and make it much more comfortable on the inside. Well, actually, before I go on to here, I say a lost art. Well, this is maybe a simplified history, but effectively, as when air conditioning was invented and heating was invented and things like that, some of these techniques became old school and perhaps were lost a little bit. It was much easier just to install an air conditioner rather than figuring out how do we take the natural airflow and keep the building cool. Now, some new ideas that have been gaining traction in the last maybe decade or so is, for example, to just plant a garden on the roof of a building. There's a program in Chicago to do this, and I believe one of the first buildings was their city hall, and they planted 20,000 square feet of plants on the top of that city hall. Now, the idea here is essentially to keep the roof cool. And of course, if the roof is too hot, then the heat comes into the building and it makes it more difficult to keep it cool. And apparently, by just planting a garden on the roof, you can keep the roof up to 70 degrees cooler than it would be if you didn't have such a garden. And for those of you who are familiar with Chicago, you know that in the summer it does get quite hot, and the roofs can actually even get up to 150, 160 degrees or so. And by having the plants there, it's much cooler and less energy is needed to keep the building cool. Now, of course, also, if those of you who are familiar with Chicago, you know that it's a bit of a windy city, and it also gets quite cold during the winter and so on. And so they put a fair amount of effort into deciding which are the best sort of plants to put on the roof for this. But they've essentially figured this out, and it's becoming a program that's more widely used in the city. Another new idea, this is in a section of Amsterdam. There's a man-made lake where it's actually a relatively deep lake, and they take water from about 100 feet below the surface of the lake, which is on the order of 40 degrees Fahrenheit or so. They use that water to cool another supply of water, which is then pumped through buildings. And this acts as, I call it a cold radiator. It's basically the same idea as a radiator where you pump hot water through and the heat radiates out to warm your building. Here you're pumping cold water through, and so that allows the buildings to stay cooler. And at the moment, this provides air conditioning for on the order of 700,000 people in this section of Amsterdam. My understanding is that they are in the process of expanding this program. Okay, so the topic that I'm mostly going to be focused on is controlling airflows inside of a building. So the goal is to design and actively control the airflows to improve ventilation and the efficiency of either heating or cooling of your building. And the approach is going to be to develop these low-dimensional models or reduced-order models which capture enough physics to be meaningful, but which are computationally inexpensive and allow one to develop control strategies to get the airflow to do what you want. Okay, so I need to go through a little bit of technical stuff really quickly just to give you an idea of how we go about doing this. The technique that I'll focus on is called the proper orthogonal decomposition. What you do is you take a set of snapshots of the velocity field of your airflow of interest. And this could be generated computationally, or if you're able to make measurements, you could do it that way. And you want to find a basis of so-called POD modes. POD stands for proper orthogonal decomposition. This is a set of coherent structures, or sort of bulk structures in the flow, which maximize the projection of these snapshots onto the modes. Okay, what's nice about these POD modes is, okay, they're orthogonal. This allows one to develop models in a nice way. They individually satisfy the sorts of things that the total flow satisfies. For example, if you have an incompressible flow in your set of snapshots, then the modes that you get out are incompressible. And if you have a set of boundary conditions you want to satisfy, then your modes satisfy that as well. And perhaps the best thing about POD modes is they have an optimality property, in the sense that for a given number of modes, the energy captured by the basis from this proper orthogonal decomposition is greater than any other basis. Effectively, what that means is this is the best possible set of coherent structures which captures the flow of your system. Now, the idea behind this so-called Galerkin projection is that you have some sort of equation governing the flow for your problem, a partial differential equation, which I abstractly write like this. What you do is you expand your velocity field as a sum of amplitudes times these POD modes, substitute them into this equation, and then remember I mentioned something about these modes being orthogonal. You can use that orthogonality property. Basically, you take an inner product of this equation with a mode with a different index, or perhaps the same index, but let's say it's a different index here. And then you use this orthogonality, which collapses the sum, which is actually an infinite sum, to a single term. And ultimately, you get a set of ordinary differential equations for the amplitudes of these POD modes, these A's. Okay, so I want to illustrate for what I call this academic example how this technique can be used. In this example, it's called plane couette flow. You have two parallel plates with a fluid in between. The plates are moving at a constant speed in opposite directions. Now, this is of academic interest because you have a laminar profile, just a linear profile, which happens to be linearly stable no matter how fast you're pulling these plates. Now, when you do an experiment for this system or you do a simulation, you find that you often find turbulent flow, in particular when the plates are moving at a fast enough speed, or for the experts, when the Reynolds number is sufficiently high. Now, from an academic standpoint, it's quite interesting to understand where does this turbulence come from, how is it related to the fact that the laminar state is stable, and so on. Okay, that's a whole other story that I'm not really going to go down, but I just want to give you an impression of how this modeling approach works. So we have a partial differential equation which governs the velocity perturbation to the laminar state. We have a system that satisfies incompressibility, no-slip boundary conditions on the plates, and so on, periodic boundary conditions in two directions. Now, just to give you some idea of the sort of turbulence that you find for this system, this is for a particular aspect ratio imposing the periodic boundary conditions for a certain domain. You have a streak breakdown process that occurs roughly periodically in time. It's turbulent, so it's not exactly periodic. This is a top view of the system, and the lines indicate contours of the velocity and the direction that the plates are moving in. The point here is that where the lines are solid, the flow is in the plus x direction. Where it's dashed, it's in the minus x direction. This is what the fluid dynamicists call a streak. Now, as time evolves, the streak develops an instability. It has a wiggle, then it breaks down and reforms roughly the same as it was before. Okay, so back when I was a postdoc, we studied this problem. We were interested in coming up with a low-dimensional model which would capture this sort of behavior, and we used this proper orthogonal decomposition procedure to do this. Now, okay, there's a lot of numbers here, not terribly important. Let me just point out a few things. So each of these rows indicates a different type of POD mode, and in this column it shows you on average how much of the total energy of your system is contained within that mode. So what we're finding is that the most energetic mode contains almost 70% of the total energy of your system. And this gives a suggestion that by understanding what's going on just with that single mode, you get a good idea of what's going on for your whole system. The next most energetic mode contains almost 25% of the energy, and then it tails off rapidly after that. So again, this suggests that perhaps by just understanding a small number of structures and their dynamics, you can understand what's going on. Now, the model we ended up taking, I indicate by the squares which modes we kept in the model. You'll notice that some of the modes, well, in particular this one, has smaller energies than some that we left out of our model. This is an illustration of the importance of understanding the physics of the problem. It turns out that this mode interacts in a certain way with these other modes that these were not able to. And so in order to get a model which could reproduce the behavior nicely, it was necessary to do this. Okay, so it does take some physical intuition and a bit of hard work, and let's be honest, a little bit of trial and error to figure out what makes a good model. Another thing I want to mention is that when you do this Galerkin projection, you're effectively throwing out a bunch of modes. That means a bunch of flow structures from your problem, and we found it necessary to include terms in our model for the modes that were thrown out. Okay, just as a comparison, so the DNS, so this is from simulating the full equations. This is what our model showed. Here, when I do the full equations, I'm projecting just onto the modes that we kept in our model. It's basically the same picture I showed you before, but projected. The point here is that we have a nice comparison between the model behavior and what we find from simulating the full equation. And the model is this low-dimensional model or reduced order model. It's much easier to understand what's going on with this and perhaps to design a controller for this than for this. Okay, so just an overview of the procedure here. So we take snapshots of our flow. We do something, okay, we solve an eigenvalue problem to get the POD modes. Then we do this Galerkin projection to get ordinary differential equation models. And then we can apply techniques from the well-developed theory of dynamical systems to gain some insight into the turbulence. Okay. And furthermore, because we have a low-dimensional model, this suggests that we may be able to develop control algorithms. Okay, so my hope here is just to give you a little intuition about how this procedure works and hopefully convince you that it can actually work for a problem of academic interest. Okay, so how would you apply this to an industrial example, in particular designing a high-performance building? I should mention that the slides on this part are adapted by some slides from Amit Surana from United Technologies Research. Igor mentioned United Technologies. They're very interested in these sorts of problems. The issues that we're interested in addressing are, for example, for normal building operations, we want to optimize comfort, air quality, energy efficiency. For so-called emergency operations, you might want real-time information on how a contaminant or smoke is propagating through a building. This information could be used to support first responders and perhaps inform some evacuation strategies for your building. Now, this is made challenging because the flow inside a building is not well mixed in any way. Okay, you have some sorts of coherent structures. I mentioned this in the context of the academic example. You have some sort of coherent structures which sort of dominate the flow pattern. Okay, so if we can understand these structures, then we may be able to understand the effect they have on the transport of heat, smoke, contaminants, and things like that. Okay, so coherent structures, and this is, maybe I should emphasize again, these POD modes, they're structures in the flow that capture the energy in some optimal sense. And so it's important to understand how the coherent structures affect things like mixing within a building. They may inform strategies for where to place sensors, how to actuate in order to perhaps control the airflow. They can be used for reduced order modeling and feedback control of mixing. Okay, so just to give you an idea of the sorts of equations that one has to solve in order to apply this to a building, this is essentially like the academic example, but for a building you're also interested in the flow of heat, so we have a temperature equation as well. Typically we use something called the Boussinesq approximation in order to do this, which is sort of a simplified, these are the equations, they're simplified over the full equations. Then what you can do is you can expand your velocity field and your temperature field in POD modes, do the same sort of thing, do a Galerkin projection, get a low-dimensional model. Now, in the academic example, we were essentially interested in the long-time behavior of the system and understanding the sort of nature of the turbulence as time goes to infinity and so on. For a building, well, you may not care so much about how the building behaves next year. You want to know right now what's going on. And so here it's important to know what are the initial conditions of your problem, and then you can feed those into your low-dimensional model and make some estimate of what the flow is going to be like over a short-term horizon. How do you figure out what initial conditions to use, or what, say, the current conditions are? Well, that's where sensors would come in. Okay, and so, for example, a paradigm you might imagine using in order to have these low-dimensional models inform your understanding of the airflow is you use sensors to determine initial conditions, what the current state of the airflow is. You feed that into the low-dimensional model. That makes a prediction of what the flow is going to be sometime later, and then you actuate in some way. You figure out how to change that flow in order to get it how you want. And then the sensors read sometime in the future, perhaps a minute later or something like that, and then this process repeats itself. Okay, so as an illustration that this proper orthogonal decomposition might be useful for a realistic sort of situation, let's imagine we have a three-dimensional room, and we have a vent with some inflow, a vent for outflow, and then we have heating elements along the floor of the room. Okay, now we can simulate this sort of system, then do a proper orthogonal decomposition, and just in terms of the average kinetic energy contained in certain numbers of modes. So the first mode, when you do this procedure, contains roughly 90% of the energy. So just by understanding sort of the very coarse overall flow of your problem, you're already getting almost the full story. And if you keep two modes, then you're up to around 99% of the total energy, and so on. Okay, now, as I mentioned, typically you would want some sort of sensors which are placed within the room that you can use to determine what the current state of the system is, use that to feed in as initial conditions into your model. Where you place these sensors, well, it could be informed by understanding what the flow is doing and so on. Let's just imagine that they're placed right here. What this is illustrating is that just by placing two sensors like that, you can figure out, you can make estimates of what the amplitudes of these different POD modes are. So the blue is for the full problem from simulating the full partial differential equations. The dashed lines comes from just estimations from the sensors. The point here is that these lines are very close to each other. So just by using these two sensors, you're able to get a good sense of what the flow is doing. And then once you know what the amplitudes, these A's are, you can reconstruct the velocity field. Remember, we expand the velocity field as amplitudes times POD modes. And okay, so this is an X slice. Okay, it's just a constant X value, what the flow is doing in the room. The DNS, direct numerical simulations, this would be viewed as the correct answer. And then the model, based on the estimations and reconstructing the velocity field, well, by eye, these two look quite similar. So again, this suggests that just by understanding what's happening with two modes, and by getting this understanding from sensors, you get a good idea of what the flow structures are within the room. Okay, and these are just different slices, constant Y and constant Z. Again, by eye, these things look almost identical to each other. Okay, now for mixing applications, this could be important for contaminants or smoke, or also just mixing the heat, making a room sort of uniformly a single temperature. It's useful to study something called Lagrangian coherent structures. These are underlying structures in a flow that dictate the transport and mixing properties. Effectively, what you're doing is you're dividing your flow up into regions where you have something like a vortex and regions where you have more kind of stretching type of behavior. Okay, so there's a well-developed theory of how to calculate Lagrangian coherent structures if you know what your flow field happens to be. And just to give an indication for this same three-dimensional room that I mentioned before, what you get from this type of analysis. Well, I know I have a lot of acronyms and I don't want to go through things in huge detail, but there are so-called direct Lyapunov exponents or finite time Lyapunov exponents, which characterize to what extent nearby fluid particles move away from each other, or do they stay close to each other. And so given a flow, you can calculate this, and the dark region in this plot sort of indicates the boundary between vortical regions and regions of stretching. And then George Haller, who until very recently was at MIT, developed a related concept which allows you to figure out where there are vortices in the flow. Obviously, these two pictures are related to each other. And here, the dark regions correspond to vortices. So in the context of the three-dimensional room, well, the flow is sort of circulating around here. From a mixing standpoint, that may not be desirable because contaminants or cold air or whatever might get trapped within this vortex. Very similar, I guess, to what Igor presented in his movies as well. Another little vortex here. Now, by heating, you may remember there were heating elements along the floor of the building. For moderate heating, you actually get a time-dependent flow. This is just a single snapshot of these direct Lyapunov exponents and this measure here. The big difference is instead of having a big vortex, things are getting stretched out much more nicely, leading to more efficient mixing. And if you have even stronger heating, well, it looks sort of like you have a big vortex here, but this is time evolving, and everything mixes together very nicely. Now, to make a connection with the low-dimensional modeling and Lagrangian coherent structures, if you calculate these direct Lyapunov exponents from velocity fields found from the full simulations, you get something like this. If we now just consider one POD mode and do a velocity reconstruction, determine the Lagrangian coherent structures, you get something like this. The point here, well, for some reason this looks skinnier to me than this, but other than that, these two look virtually identical. So again, this suggests that maybe just understanding the dynamics of a single mode is sufficient to capture the transport properties for your problem. Okay, so looking forward a little bit, well, so I gave this brief historical perspective. There are different methods of doing things like keeping a building naturally cool. I think that a very promising approach is to use techniques from dynamical systems and control, and in particular doing these reduced order models of the airflows. You put this together, very promising approach for building more efficient buildings. But certainly the problem is not done at this point. It'd be nice to develop better low-dimensional models. I alluded to this. We found in the academic example that when you model the losses to modes which are not included in your truncation, you can get a model which behaves much better. Okay. Furthermore, well, in the academic models, we were mostly concerned with the long time behavior, but for these building applications, it may be better to design models which just minimize error over some specified time interval. Remember, I mentioned that you could use sensors to continually monitor what the state of the system is. That sort of resets your initial conditions and so on. So you may just care about your model being correct over the time interval up to the next sensor reading. The POD modes are optimal in an energetic sense, in the sense that they capture, on average, more of the energy than any other basis. But if you're interested in mixing applications, then you may want modes which optimally capture the mixing properties as well. Okay, so I think that there's a lot of opportunity for trying to develop a framework for finding modes which are based more directly on Lagrangian coherent structures. And then, of course, well, the room that I showed you the sort of preliminary results from is a nice room. There's no tables. It's very simplified, no windows, anything like that. And it's also a single room. What happens when you start having rooms connected by vents and hallways and things like that? Do we do a proper orthogonal decomposition on each room individually? Do we do a proper orthogonal decomposition on the whole building? Is there some way of doing it for the individual rooms and connecting those results together in a nice way? Optimal sensor placement and estimation, maybe let me just go back to give more on this. Well, for example, if we have a room here, so we have a vortex here and a vortex here, and we want to understand, is there a contaminant or something within this room? Well, as a rule of thumb, you would say, well, I need to place a sensor kind of inside this vortex because this is just recirculating. I need something inside this vortex and perhaps something outside of the vortices. So you might say, well, I need 3 sensors in order to know for sure that there are no contaminants in this particular room. Well, maybe that's the case. Maybe there are better ways of placing things. But by understanding these sorts of airflow dynamics, and in particular the Lagrangian coherent structures, it gives some indication of, okay, maybe this is where we should place sensors. Okay, and then finally, looking forward, ultimately it would be nice to use sensors and an understanding of the flow dynamics to be able to optimally control the mixing properties of, again, things like heat or understand situations of mixing for contaminants and so on. Okay, so this is certainly ongoing work. I mentioned United Technologies, which has been quite interested in this problem, and just to remind you, the slides that I showed on that are sort of adapted from some slides from somebody who's working there. But I think that it's a very sort of exciting problem. These are issues that are of industrial interest, but also of academic interest as well. And I think the time is right, given the context of global warming and just wanting to save money on energy, for everyone to work together and figure out how to make the buildings better than they are right now. So with that, I thank you for your attention.
Thank you very much, Igor. In addition to what you said, you could also mention that I've had the pleasure of being here in Santa Barbara since the turn of the century. What I wanted to talk about today is to give a controlled perspective of this. And you already have heard a build-up of this from from Igor and from Jeff. So I'm going to talk about challenges in control of buildings. You've already heard from Igor that there are tremendous potentials for energy savings. There is also right now a strong national and public interest. There are useful technologies around the corner, and I will talk about control technology in particular. And the things that are coming up are network modeling and control. And I think there is a big change in life cost of control systems, because heating, ventilation, air conditioning has been the sort of development country of control. And now, for example, it's changing because the major control companies are now getting contracts from companies like IBM to be responsible for all their energy in their factories, for example. And that totally changes the attitude of people. You are no longer selling equipment, you are selling a service that's going to save energy. And what I'm going to talk here after this introduction is that I was very heavily involved in this a long time ago. And I think there are some lessons we can learn from this project. So that's why I would like to mention this. That's what's called long time and far away. Far away means it was made in Sweden. Then I'll talk a little bit about control to give you a perspective about what's happening in control and things that we can capitalize on. And then I will move to the challenges that we have in building. So in 1968, I had been appointed 3 years before as professor of a new department of control. And that was a department that had global responsibility for control all across the university. And at that time, it's hard to believe, but computer technology was just starting. For example, in end of 1968, there were 1,800 computers controlling systems all over the world. So there was a lot of interest in doing this. And I had a past experience of that from IBM. So I was interested in looking at control technology. Also, we had an interest to see what we can do in different areas. And this was also a time of energy crisis. So there was a lot of interest in energy in buildings. And we looked into building control. And one reason for this is that the processes in building control are slow. And computers that time was also slow, so it was a good way to practice computer control in it. We were also interested in doing automatic modeling from data, because we realized that to control of this system, it was impossible to derive models from first principles. Now, of course, the situation is very different, as you heard from Jeff. But if you step back at this time, we were interested in pursuing a technology to develop models from data. And building systems were a good case for that. The result of this, the lasting result, is a company that is in Malmö, far away from Lund, has about 5,000 people right now, and we were involved in getting that kind of activity started. We also were awarded, 15 years after the project, we were given the Large Energy Prize for energy-saving ideas. So it was recognized that what we did had some impact. I've already mentioned that we wanted to do computer control. I also said that we were interested in using networks, because I had previous experience of that from IBM. We were actually doing remote control of processes over quite long distances, using very primitive modems. And things actually worked quite well. They went through a manual telephone exchange, and it worked very well until the lady in the telephone exchange started to ask us, "Are you still calling?" And then everything was broken down. So that was a technology we were interested in doing. We were also interested in doing interactive software, because when you're sitting and working with systems online, it was very nice to be able to change things online as you were sitting there without having to do recompilation. The reason we picked HVA system, it was possibility to have a significant impact. Dynamics was low. We established in a very early on contacts with industry, the suppliers of HVAC equipment, both domestic and foreign. And one thing we did is we started an educational program to educate people about using control for the devices that we're having. And because of this, we developed a very good contact with industry. The system characteristics, they were inexpensive, low-cost actuators and sensors. They had nonlinearity, friction, backlash, and hysteresis. Dynamics change with time and operating conditions. And the loops we were looking at were mostly single loops, and they were using very simple controllers. That's one of the major challenges today when we're going to tie many loops together. So that's a very different business. The milestones we had is where we were very successful in doing the networked experiments. So using a computer at the university department, we were controlling temperatures in buildings all across the local area. And we showed that this was a feasible technology. We were very lucky because we came in contact with a startup company who was starting to use mini computers for commercial buildings. So we started a collaboration with them, and they very quick, at that time, there were none of the big commercial suppliers had computer control of them. So he was able to install it in quite a few buildings, and then later on it was acquired by several other companies. We started industrialization. I will speak more about this later on. We also got ideas for new research, because we saw that for these buildings and with the personnel you have running them, there was a big need to do automatic tuning of the controllers. I have a slide here to illustrate this. This was the traditional academic dress of professors in Sweden a long time ago. So they dressed in tails when they were lecturing. So what we wanted to do in here is that we wanted to build some of the knowledge that a good control engineer have to build it into the devices. And that was an idea we got when we started to work with heating and ventilation systems. This developed into a very fruitful research line that has resulted in quite a lot of patents and quite a lot of products. So the standard products we have right now, they have a lot of this technology built into it. You just push this button, and then this controller tunes itself. So that was a useful spin-off. Some observations were made is that systems change with seasons. There are many simple loops. The personnel who are handling them are not experts at all in control. And this showed us that there were some areas in control which were not looked at the time. Mostly it was focused on modeling and design. But in here, there are essential problems in commissioning and operation. And there are some very challenging research issues in that area. And also the idea that we were using remote supervision for energy savings. The technology transfer, it went through the courses, and then we had a very influential company in Sweden called the Wallenberg Group, and they had major controlling interest in Ericsson, Volvo, ABB, etc. And they also had research councils. And through this research council, there was a lot of networking going on. So this small company was later on acquired by another company, and it was taken private. It has went through quite a lot of successions. And several of our PhD students, and also master students are working in this company. Right now it's owned by a French group that's called Schneider. The lessons we learned is that we went into this, we had research funding from the building council that was long range. We were essentially promised that if we are doing well, we could continue to do this for about 10 years. We had broad student participation at many levels. We were looking at industrial collaboration and networking. And we were also quite flexible in looking at opportunities. So for example, one of our PhDs, we loaned him to this startup company to work half-time with them for 2 years. And we said that that was, so to say, a good collaboration to do. Then we stopped. And why did we stop? Well, we had been doing this for 10 years, and since we have area responsibility of control, our philosophy was to work in application areas and switch application areas over time. And also one of our students became a professor in building systems, so then it was natural that he was going to take on it. And also technology was changing, and we felt that it was time to move on. So now I'll tell you a little bit what's happened in control since that time. Here's a quick one. Control emerged during the World War as a need to develop military systems. A nice thing was that there was a holistic view of theory and application, and it led to a very widespread education. Very quickly after that, we got into a second phase driven by the space race, where mathematics was coming in, computers were coming in, and there was a rapid growth of subspecialities. And we learned a lot about optimal, stochastic, nonlinear control, etc. We got computational tools and a fantastic development of theory, but the holistic perspective was lost. And my belief right now is that we are entering a third phase. The drivers are embedded systems, networks, and also an interest in control from other sciences like biology and physics. Other keywords are autonomy and distribution. We would like to have systems with a high degree of autonomy. There are exploding applications. And my hope is that in this process, we will recover the holistic view again. And I think to do this, we need to have projects like control of buildings and similar things in order to be able to do this. Why is control useful and why is it so general? Well, here are some of the examples of the power of control. One of the most important things is that feedback allows us to make precise systems from imprecise components. Secondly, we can reduce effects of disturbances and component variations. We can regulate, stabilize, and in general shape dynamics. So these are all good things. Now, what are the drawbacks? Well, whenever you are closing a feedback loop, you run the risk of causing instability. And that's one of the reasons why stability theory has been such a prominent aspect of control. Another side effect is that whenever we're using sensors and feedback, we are feeding sensor noise back into the system. So we have to keep control of how much sensor noise we are feeding into the systems. But on the whole, that's quite a list of things. And that's the reason why feedback and control is so widely used everywhere. And just to give you a feel for this, if you look at process control, this is a paper factory which can have about 5,000, 10,000 control loops, and the factory would not function without them. Here's an oil refinery, which is very similar to paper mills, and here's a steel mill. It has fewer loops, but the loops are much more sophisticated. You look at discrete manufacturing. Here's a car factory with a lot of robots, and extensive use of control. You look at consumer electronics. You have the Segway, you have the cellular telephones, you have the CD players and the things. They are filled with control, and control is mission critical, for example, for all the CD players and the DVD players. Vehicles. Going from the aerospace industry, rockets, to UAVs, to ships, to vehicles, and to aeroplanes. And I heard on public radio this morning that in the consumer evaluation of cars, now for the best car, they're only looking into cars that have what's called ESP, Electronic Stabilization Program. And of course, in the cars that you drive, you all have speed controllers in them that keeps the speed constant. Control is also entering other arenas, and biology is currently a very hot topic because systems biology is now a major activity, not the least on this campus. But it has a long tradition. Schrödinger wrote a book already in 1944, What is Life? Wiener wrote a book on cybernetics in 1948. Von Neumann wrote a book, Computer in the Brain, in 1950. One of our control mathematicians started a journal in 1967 called Mathematical Biosciences. I think one difference that we are experiencing here now is that in biology, it's much more quantitative. So I think chances of doing things in biology are much larger today than what it used to be. So that was a little bit about control. And now let's go back to buildings and challenges. There have been three very interesting reports published recently. This is a study from the National Academy of Engineering called the Engineer 2020, where they asked, what does engineering look like 2020? This one here tells about educating the engineer 2020. Assuming that this is correct, how should we change the engineering? And this is a study that was financed by the Air Force Office of Scientific Research that was focused on control. And it's called Control in an Information-Rich World. So they all give indications about what is happening to our field. And now if we start to look at the new challenges we have, and these are systems that are rich in sensing and actuation. And you have already heard this from Igor. He mentioned that in buildings right now we can expect lots of sensing sitting in them and lots of actuation sitting there. And the methods we have developed in control and that we've been using so well, they don't work so well for systems that are rich in actuation and sensing. So we are needing new techniques for that. Another thing is systems with a high degree of autonomy. Igor already mentioned this, the intelligent buildings, and there are tremendous challenges we have. And when you start to make this system, we have to introduce adaptation, we have to introduce learning, and we have to introduce cognition. Coupled to that, we have to look at control of networks, because that's the only way to connect the sensors and the actuators into this. And then we also have to look to the architecture of these systems, because these systems have to sit there for a long time, and they have to be able to operate safely. So the question is, how do we build this system and how do we architecture them so that they can be operated and run over a long time in a very safe way? So I said that the reason we went into heating, ventilation, air conditioning 40 years ago was that we wanted to exploit computer control and we wanted to exploit automatic modeling. Now in here you see a whole list of very challenging research problems that the whole control community is struggling with. And I think going into building system is an excellent way to start to understand many of these issues which have applications way outside the building systems. So here's a picture that you have seen before. It's a picture about buildings. And just to look at a few systems you see in here, we have the natural ventilation, we have the windows, we have the indoor environment, we have the elevators, we have the safety. We also have to be concerned with vibration damping. That I know is a field that is very close to the heart of the chancellor of this university. And of course, to do this and tie it together, we have to use the sensing, actuation, and the communication networks and the controls. Now, the drivers for change that we see is that the energy costs, the public awareness of global warming, which I think is a very strong driving factor. Another thing I think is important is changes in building codes and standards, and also the change that we have in business structure, where, for example, for commercial buildings right now, the control companies, as I said before, instead of delivering components, they now have to deliver services of keeping the energy low. Just to give an illustration, this is a quote from LA Times last week, where they said that the two city council committees voted to require that all major commercial and residential developments slash projected energy and water use. So in other words, in the building codes right now, there are coming in requirements. There's a nice parallel of this when it comes to cars. It was the California rules for emission that started the trend to introduce computers into cars, because introducing feedback into the car engine was the only way to lower the emission. And now we see what's happening to cars when you started to introduce computers into them. There may be very similar things happening in buildings. And also, because the car industry was so large, it was a strong driver for technology. So that's why we got microcontrollers and other components from it. Here's a quote from the Engineer 2020, where they say that in the past, increases in knowledge spawn within new microdisciplines within engineering. But the contemporary challenges, they all require a systems perspective. And control is, I claim, it's the first system science. So that's clearly an indication of the importance of control in this. The way I view this is that if you look from a control perspective, in order to do control well, we have to interact with the physics of the system we are trying to control. We have to interact with computing because that's how we are going to implement the system. We have to communicate because we have to communicate with sensors and actuations. And then, of course, we have always had a strong interrelation here with mathematics. That poses big challenges because we need to create people who can work in this environment. This means that we have to make sure that the engineers we educate, for example, in control, they know enough about physics so that they can interact in a sensible way with the people who know the physical nature in here. The same thing here is with computing. Since we're going to use computers, people in control have to be aware of this. Similarly, people in computer science and control, computer science have to be aware of the issues that have to do with control. This means that we have to pay a lot of attention to education. And in particular in the new fields, like control that's only 50 years old, computer science that's even younger, we have what I call the dilemma of emerging fields. We've been teaching everything we knew. As we know a little bit more, you add another course, you add another course, and you add another course. And this is not viable because we have to sit down and filter out what is the essence and then take away the things that are less important and focus on the fundamentals. So I think to cover the systems perspective, I think we certainly have to redo a lot of the education that we are doing. I will bring up one specific area here, namely the area between control and physics, where we have a lot of model building going on. And here is what they say in the Engineer 2020 about modeling and simulation. That there will be growth in areas of simulation and modeling around creation of new engineering structures. computer-based design build engineering will become the norm for most product designs, accelerating the creation of complex structure for which multiple subsystems combine to form a final product. Igor has already mentioned the 707 or 747, which is an example of this. I will give you another small example. This is something that was done by two of my PhD students. They worked at UTRC in Connecticut for 5 years. Then they went back to Sweden and they started a company called Modelon. And they persuaded the major car manufacturers in Europe to get together with their suppliers for air conditioning for cars. Now, an air conditioning system has many components. It has compressors, it has evaporators and other things. And the car manufacturers are buying them from different suppliers. Now, a system like this, you will never know if it works until you connect it together. So what they have done is that they have persuaded the component manufacturers to deliver not only hardware, but also a validated dynamical mathematical model. And then the car manufacturers can then run their simulator and ask, what's happening if I'm replacing this component from that manufacturer with the same component from another manufacturer? They are using a software environment that's called Modelica that was also developed in Europe. The particular implementation of that, incidentally, was the one that was used extensively by Toyota to develop the Prius. Of course, when you deliver a model, you run the risk of giving away intellectual property. And this is handled here by doing extensive encryptation. So I think UCSB is ideally positioned to do this kind of work in the building area. I think the long tradition we have had here of doing multidisciplinary work is absolutely necessary to succeed in this. There are major strengths in the areas of control, dynamical system, computation, and fluids. There is a center for control, dynamical systems, and computing, which is an excellent platform to create this work we have in here. And also there is good long-term experience of working with industry. So if you look back to the project I did 50 years ago, the possibilities to do a project here on building system is infinitely better than it was when we started to do here. So I'm extremely optimistic about the initiative that's been taken in here. So what I've done here, a quick introduction. I spoke about the project done a long time ago. I told you a little bit about advances in control. I spoke about challenges in building control, and I came to the conclusions now. I think this is a good time to look at control of buildings. Time is right. We clearly have a systems challenge. Modeling is very important, and the thing that Jeff was speaking about to develop a reduced order model is very, very important. These systems require network, and they are very rich in sensing and actuation. Thank you very much.
Thank you, Igor. It's always nice to come back to Santa Barbara, but whenever I come back, I'm fascinated by the intellectual content of what's out here. But I also get lost by the traffic changes that happen. And there's so much of construction that has happened that it's a new place. It's been about 11 years that I've left Santa Barbara, and of course the place has completely changed. So thank you for inviting me out here. Before coming here, I spoke to Igor and I said, what should I talk about? Should I talk about my own work or talk about something that I don't know much about? And he said, talk about something that you don't know much about. So that's buildings. But before I do that, I will just very briefly present a result that came out of our lab, which we are very excited about. And that is in the area of energy conversion, thermoelectric energy conversion. I work with John Bowers and Art Gossard. We've been working for the last 10 years in this area, and this is a materials problem. And what we have found is that, and this is a paper that just came out in Nature, that you could do the same, you could get the same performance as you would in exotic semiconductors now in silicon. And that hopefully would be very useful because you have a $100+ billion industry which focuses on silicon, could divert its attention to heat engines and refrigerators and air conditioning. So that's something that we are quite excited about. But that was just one slide. So, curbing the energy demand in buildings. Let me give you a perspective, and this is, as I said, it's new to me, but we have been looking at this, the energy issues at Berkeley for some time now, and trying to take a sort of holistic approach of what is needed. And there's been a lot of work that has gone into the supply side of energy, which is fuels. And BP has put some money, and the DOE has done that as well. But I think the lowest hanging fruit in the energy game is really on the demand side. And what I'm going to talk about I think is the lowest of the lowest hanging fruit, which I think is in buildings. So let me explain. So if you look at the energy problem on a global point of view, this is a paper by Marty Hoffert in Nature that came out in Nature. The real problem is population. And here is, here is the population growth. This is nonlinear out here. And whoops, this is almost dying. And today we are at about 6.5 billion people. The population will, I think, saturate, at least United Nations thinks, saturate about 12 billion people or so. This is GDP per capita, which is increasing linearly, which is we are producing more per person, which is great. It's in the right trend. The next one is watts per GDP. How much energy do you use for a given unit of product? And that is going down, which is great. That means we are being more energy efficient. And the last one is carbon per joule. How much carbon emissions do you have per unit of energy that you use? And that is going down, which means we are less carbon intensive. Everything is in the right direction except the population curve. So if you take the product of the first three, you get the total power usage. And if you take the product of all four, you get the total amount of carbon emissions. And if you do that, you find the graphs are not very forgiving. That is, the total power consumption is going up in a linear fashion, and the total carbon emissions are increasing linearly. Right now, we're at about 8 gigatons of carbon per year that we're emitting, and that is going up linearly. And the idea of being linear is actually, when you emit carbon in the atmosphere, it gets accumulated. The biggest sink are the oceans, but still you can say that you just integrate a linear curve and you get a quadratic. And that is what is happening, and it's a cumulative fashion, it's accelerating. And that is the real issue that we are faced with. It's not so much the availability of fossil fuel. There's enough coal for enough time, but it's the CO2 problem which is more troubling. So the IPCC report of last year, IPCC, by the way, is an optimistic approach, outlook of energy and environment. The situation could be actually much worse than what the IPCC predicts, because there are some positive feedback things that are not included in the IPCC. They always sort of water it down so that everyone, the United States, Washington, D.C., can accept it. And here's the thing: if you want to take that linear and turn it around, and this is actually the CO2 concentration. This is the quadratic part. If you are to, so let's say, stabilize at 550. Today we are at 380 parts per million. That's the emission curve that you want to have. That means there's an inertia in the global system, but you want to turn that around and you want to reduce your carbon emissions. The question is, how do we do that? And there are two ways of doing it. One is changing the supply side to more renewable, and the other is to reduce the demand. So there has to be an impedance match at some point to be able to sustain, the development. So if you look at the supply side of just the United States, this is the supply side. This is primary energy. This is electricity generation. 50% is from coal. This is natural gas, petroleum, and this is nuclear. And so these are all carbon emitting ones. Petroleum is very small for electricity generation, but of course it's a large amount for transportation. So this is, if you want to reduce the carbon emissions, this is the supply side. You have to increase this side more, which is where all the renewables come in, but that's part of the story. You have to increase this side up, but you also have to reduce the demand so that there's an impedance match. So the question is, where do we consume energy? And so this is the US energy consumption. It's about, as Igor had pointed out, it's about 40% in buildings, roughly 1/3 buildings, 1/3 transportation, 1/3 industrial processes, which is mostly steel, glass, cement, paper, a lot of which goes into buildings and transportation. So that's where we are really. And of the buildings, it's about half and half between residential and commercial. There are, of course, 60 million residential homes in the United States, and there are about 5 million commercial buildings. So if you want to look at energy savings and you want to go for the biggest bang for the buck, commercial building, because you can have an influence much more quickly if you do the right thing in the commercial buildings. So that's where we are really focusing on, is let's cut the chase and go try to save energy as much as possible. So if you are to look at this commercial building, what are the real problems? And you already heard some aspects of that. And this is what we're trying to do. So this is, again, reliving the 70s. And I think, as Carl pointed out, this is the 1970s being rewound and turned again in a different way, because we have some technologies which were not there in the 70s. But the issues of the energy and environment, and when the crisis hits you, it's reliving all that. And it's actually, I'm glad to see that happen within 30 to 35 years, because we can then get the expertise of people who were there in the 1970s now. And I think we just heard part of that earlier. So this is things which had happened in California in the 1970s. So here is US per capita, the per capita electricity consumption in the United States. And this is what is the United States over the last, from 1970s till now, whereas this is California. So California flattened out at about 1972 or so, and it remained flat. Now, this is often called the Rosenfeld effect. Art Rosenfeld, who is now the California Energy Commissioner, he used to be he still is a physics professor, particle physics, the last student of Enrico Fermi. And he thought in the energy crisis he'll devote about 2 years to energy and go back to particle physics. And those 2 years are still not complete yet. He's now still working in energy and now the commissioner. And one of the things that he introduced, he built, it's not just Art Rosenfeld, but many of his team that he put together, looked at buildings as one of the primary savings in energy. And things that they did at that time, this is an example of an appliance standard that changed the ball game. And this is just refrigerator standard. And as an example, here is average energy use per unit of refrigerator. And this, you look at 1970s, and the energy consumption per unit going up and then going down. And this is the size of the refrigerator. And the size has actually not changed, and in fact it has gone up. And it's limited today by the size of the door of your kitchen. That's what sort of limits what the size is. That is, that's sort of, it's increasing a little bit. But the energy consumption per unit it's gone down by a factor of 4 to 5. And that is very, very significant. And this is the price. So price going down and becoming more energy efficient does not mean it's more expensive. It actually can mean less expensive. The impact of this, just this one thing, if you just compare, this is the energy the refrigerators in the United States would have consumed if we had the 1974 standards. This is what it consumes now. And this is the energy savings that you have with more and more efficient refrigerators. And if you just compare that on what you can do on the demand side with the supply side, and here is 50 million 2-kilowatt photovoltaic system. Okay, that's the energy that it produces. This is conventional hydro. This is Three Gorges Dam. So that's the impact that we're talking about out here, and that, I believe, is the real opportunity, the lowest hanging fruit in trying to do this impedance match in carbon emissions from supply and demand side. So, by the way, that's electricity use, which is only 10% of the total energy use. So the other part I didn't even talk about, there's huge opportunities in savings in other aspects also. And it doesn't mean, this is an interesting plot of Human Development Index, which is a measure that is used for in terms of education, living standards, etc. And this is electricity consumption out here. And here is United States is right out there. I mean, one is sort of the ideal living standards. And here's United States, here's Norway, Canada, etc. And these are some of the developing countries, India and China, the big energy consumers. So the question is, where do you want India and China to end up? If they end up over here, we have a real problem. What you really want to do is if you look at this graph out here, these are some asymptotic curve, you want them all to come out here. Here is California. And while we brag about the fact that in 1970s California turned itself around, there's a long way to go now, going back out here. This is, if we can get there, and all the developing countries get there, I think it can be sustainable. Otherwise, we have some real problems. So now coming back to the building side, where I think there are some opportunities, what we are now trying to do, and this is in collaboration between, right now, between Lawrence Berkeley National Lab, UC Berkeley, UC Santa Barbara, and an industrial consortium being led by United Technologies, but bringing in other industries as well. And what we're trying to do is put together a group of scientists and engineers looking at buildings, and we call this High Performance Buildings Research and Implementation Center, HyperBrick. And where we are today, and we had a meeting where Dean Terrell and Igor were there in Santa Barbara, in LBL in December, and we had the meeting of how to put this center together, what's the intellectual content of this center. So let me just walk you through what we're planning to do. We haven't done much, but what we're planning to do. So as you saw by Igor's talk, this is from the market point of view, it's about $120 billion per year of energy bill in commercial buildings. And if you could reduce that, that's a big economic driver for all this. So the vision for this is to reduce the energy consumption by 4 quads. Quad is quadrillion BTU. Unfortunately, that's the unit that is used. But it's about, 1 quad is about an exajoule, 10 raised to 18 joules. Just to sort of give you a perspective, the total energy, end-use energy in the United States is about 30 quads or so. So this is a very, very big deal if you can save 4 quads and 400 million tons of CO2. To do that, you need to reduce the energy consumption in new buildings by 90%, and the energy consumption in existing building by retrofitting by 50% across the board. This is not just one-off building. That is non-trivial, and I'll explain that. And it's not that the cost of health and comfort, you can turn off the lights and the air conditioning and you can reduce energy consumption. That's not the way you really want to do. It is improving at the same time the health and the comfort and the security, etc. So just to give you the numbers, and I think you saw that, if you do that, 90% of energy consumption in new buildings, 50% in existing buildings by 2030, that's the energy that you will save compared to the electricity generation from coal-fired power plants. So you can essentially say that we don't need half the coal-fired power plants. That's the carbon emission reduction. If you can reduce the energy consumption in buildings by this. And these are the nuclear renewables all put together. So there you can now say we may have an impedance match between renewable energy and the demand for energy. This is United States, where the square footage of commercial buildings is growing at about 1.7% per year. In China, it is growing at 7% per year right now, and right now, the square footage in commercial buildings is higher than that in the United States, and is growing even faster, way faster than the United States. And it's going to grow about 3%, projected 3% about, from 2010 onwards. In India, it's about 1/10 that of China in terms of commercial building space today, but it's growing at even faster rate, 8.5%, so that by 2030, you're going to have 10 times the square footage that you had in 2005. And that is a huge, and there lies the opportunity, is that those buildings have not yet been made. If we could get in early and do the right thing in those buildings, and there's probably more interest in India and China about this than in the United States, then you can have a real impact in starting off the right way. So what do we need to do? So here is, by the way, California. taking the lead in the United States, the California Public Utility Commission, which is based in San Francisco, are coming up with mandates for commercial buildings and residential buildings. One of the mandates is that by 2030, all new commercial buildings will be zero net energy, okay? And you want 50% retrofit, 50% energy reduction in the retrofits. So what I talked about, 90% and 50% earlier, as our vision, it's not an accident. It is perfectly aligned with what California wants to do, and California's vision is perfectly aligned with us. And it is, while that's a very laudable goal, we need to get there. The technology roadmap to get there is not quite certain. And that is something that we can provide as scientists and engineers, is what is the roadmap to get there? So we know what the milestones ought to be. So if 2030 is where we want to go, this is American Institute of Architects and California Public Utility Commission, this is the goals, then I won't go into the details, but here is something that we are coming up with right now. In the next 3 years, what do we need to do? 5 years, 8 years, 10 years, and then how do we get this implemented and deployed in all the in the whole industry? And this is sort of a market transformation that has to happen, which is not easy because there are a lot of stakeholders. The building industry is very, very fragmented. So while we develop our technology, which is necessary, that's not sufficient because we have to engage the buildings and industry, et cetera. So what are the real challenges? This is what is happening today. I mean, I often use the analogy of cars. So if you have a car today, let's say I have a Camry from 1995, I have a certain energy consumption in the car, and to improve it, I can take it to the mechanic and do a tune-up. All right, so I can change the oil, I can do a tune-up, idling, RPM, and maybe I can put a piston ring, okay? And that increases the energy efficiency by about 10% or 15%. But that's about it. You cannot get the 50% reduction in energy consumption like a Prius may have. You can only do that much with existing cars. So that is what is going on in buildings. ESCO companies, energy-saving companies are going into buildings and retrofitting and doing a commissioning, et cetera. You can get about 10, 15%, but that's about it. And that's where it is widely deployed, and that's great, but you can only get that much. So in terms of deployability, it's wide, but it's very shallow in how much energy reduction you can get. On the other hand, you can design this one-off building with zero net energy. There are about 4 or 5 in the United States right now. But that's about it. You cannot, that's only 4 or 5, and you have 5 million buildings, commercial buildings in the United States. What you really need is to do both. Otherwise, you're not going to get where we want to go. And that, as you heard already today, need a systems approach which is scalable and deployable. And for that, you need the right tools, et cetera, and I'm going to come exactly what we are trying to do. So you already heard some example. Here's some example of a new building design, and this is by United Technologies in China. And what they did out here was they took the daylighting, and they took the shading, the radiant heating, high performance, this is carrier chiller, which is supposed to be the best in the industry, and some energy recovery by heat exchangers. And they took individual components and pushed it as hard as they could, and they got about 25% in energy saving, but that's about it. And what was not done is the integration of all these components, and the question is, can we do that? And what is the mode for doing that? And I think there's opportunity. These are necessary, but not sufficient. And the opportunity is really to integrate the system to go the next level, which is the 70 to 80% reduction in energy consumption. This is an example of existing buildings where you can do a tune-up, like a car tune-up, but the tune-up goes out of whack in a year or so, just like it happens in car. And then you can, broken equipment or some detuning that happens, then you can actually, if you have the right feedback controlling systems, which is great, but they've not tuned, you can actually spend more energy in the oscillations of a system than actually what you save, that you intend to save by the right control system, et cetera. So there are some gaps in the design, modeling, fault diagnostics, and self-tuning, which Igor mentioned earlier. understanding and exploiting the dynamics and control in the system is very, very important. And often it is not, it's there in few buildings, but not in all the buildings. So, and then you already heard the example about, this is a disaster example in this hotel in Atlanta, where you actually spent more energy trying to fix a problem as opposed to looking at it in a systems way. I won't go into the details of this. So what is required? So let's sit down and say, what do we want to do in terms of an integrated system? So here's an example. You have 2 rooms, all right? Just 2 rooms to start with. One has sunlight, the other does not. And you want to be able to control, you want to maintain the indoor environment, for example, temperature, humidity, CO2 level, etc. And so you want to have sensors in there, and as we heard today, there are ideal places of putting the sensors, but let's you have some sensor modules out there, and the data has to go somewhere. Well, data needs to be communicated through some network communication layer. But what do we do with the data then? Well, there has to be some intelligence, as you heard before, to be able to analyze the data. And we call this the building operating platform. And it's almost like the building is like an operating system. The building operating platform looks at the data, okay, and embedded in this is some energy analysis, which is Energy Plus, Elica, whatever you may, sort of decomposition of the problem into simplistic terms, put in there so that you can do the modeling. So what does the building operating platform do? Well, it gets the data, then thinks about it, and does some real-time optimization, and it has data from other sources. For example, if you want to do thermal storage, that means you can make ice in a basement of a building where the electricity price is low by some chillers, etc., and you could use it later when the electricity price may be high. So that data, or what the temperature or the capacity, has to be inputted in the building operating platform. The external ventilation, the outside air, which, outside air and humidity, which depends on current weather, and you may have some future weather so that you can plan in future. So that can be put into this, that's the data input. Then what do we do? Well, it has to then decide whether it can control the HVAC, air conditioning and ventilation, and then you can have some local control into these rooms, etc. But then the question is, do you really want to start the HVAC, or could you get by actuating the external ventilation into this HVAC system, or using thermal storage as a means to do the cooling, for example, as opposed to turning the HVAC? So that decision in terms of where the energy savings are has to be made at some point. Well, if you do that, well, if you are interested in heating, for example, well, instead of turning the heat pump, you might like to turn on your on-site power generation instead, because if it's a fuel cell or a micro turbine, that has waste heat. And that waste heat could be turned into this ventilation system for heating, if that's the need. But when you turn the on-site power depends on what the electricity prices are. So if you have utilities and electricity prices go up and down by a factor of 3 or 4, you might like to turn on the on-site power not when the electricity price is low, but when the electricity prices are higher. So that depends on the electricity prices, the external power, the utilities, the electricity tariffs, and the carbon emission rate. So if you're getting electricity from wind as opposed to coal-fired power plants, well, there will be a different dollar value for these in the future. So you want to decide on that and then turn on the on-site power. But by the way, this is fine, but you may be able to store the electricity, but this has to control the appliances. You don't want to keep the appliances on all the time. You might like to turn them off when you're not present. And also this lighting and windows and facade control so that you can reduce the radiant heat that may be coming in from the sun. And that has coupling with the HVAC. So you soon realize that this is a fairly complex problem. And of course, by the way, you want to do real-time optimization to be able to get to zero net energy or zero carbon footprint and minimize the cost for a building operator. That's the complexity that we're looking at, and this is a simple view. There's only 2 rooms, by the way. So obviously in a real building, it's going to be much, much more. So what do we need to get there? So we are sort of thinking hard about it. We had a good start at this, looking at the New York Times building, where LBL and UC Berkeley was involved, where this is the New York Times building. They built a mock-up for lighting and HVAC, and with controls, and this is an example of simulation out here, and as well as these are rows, these are the window out here, sunlight coming in, and these turned off and these turned on to maintain sort of a equal or uniform lighting in the building, etc. So, but this is just one start. We had a mock-up facility that you could try out all this. Going in the future, as you heard, what we really need to do as an integrated system is what I call the Prius of buildings. So what's new in Prius? Well, Prius has brakes, it has a battery, it's maybe a slightly larger battery, but it has engine, which all cars have. What is new in Prius is that it integrates the system and scavenges power from the brake, stores it somewhere, use it to run the engine when it's necessary, or when it's going downhill, take the power and store it in the battery. That's the opportunity at the interfaces of system, which has not really been done in a widely deployable way. That's where I believe the opportunity really is. And while every Prius is the same, every building is different. And that's where their complexity also comes up. So building operating platform is something that we need to do. There was a workshop that happened in LBL between LBL, UTRC, UC Santa Barbara, Berkeley, Stanford, UIUC, where some of the early seeds were sown, and now we are seeing the effects of that and sort of more an integrated approach to this. And what is really where we're going with this right now is the major project themes. So if you say that, okay, this is where we need to get to, how do you divide that into projects that need to be developed? And we don't know what those are right now, but these are the project themes that we have. Monitoring and diagnostics. We certainly need to be able to see or to understand how a building is operating. And that data needs to be there. And right now, often it is not there. And you need to be able to diagnose and self-tune, if necessary, where the faults are. So this is sort of the lowest hanging fruit. Let's put something out there to find out how a building is operating. Right now, we're going blind in many cases. You heard about the building operating platform. And this is the equivalent, as opposed to, this is not exactly a building operating system, which is completely digital and computational. Here you have a physical system attached to it. And that we really want to develop. If you want to develop a building operating platform, which is the smart building operator individually cannot handle all this data, but you need an automated system. That should be there in every building, whether it's a centralized or distributed, we'll have to decide, and there are pros and cons to both. We want to develop this as a Linux model. That is, it's an open platform. People can build on top of that, open protocols for communicating, et cetera. That is something I think would be a good thing for the whole industry, and everyone can use it then. Also, a system design tool. Eventually, architects will be designing buildings. I will not be, Igor, I suspect, will not be designing whole buildings. It'll be architects. But architects may not have all the engineering of mode decomposition and using all the fluid mechanics, etc. That needs to be built into something where it is transparent. Even my 12-year-old daughter, when they does Sims on a computer, that's the kind of tool that we need, so that you don't need to be a high sophisticated engineer to be able to design building. That has to be embedded. We're calling it building spice, sort of like what happened for IC design, the spice model. And it has to be public domain so that people can actually get to use it. There could be packaging that happens, and proprietary packaging makes it easier and all. That's later on. But it has to be public domain to start with. And of course, integration enabled component level. So if you're developing lighting as well as HVAC, it should be developed, and solid state lighting has to be developed, there's no question. And high performance HVAC has to be developed. But should be developed in a way that there are interfaces that you could then connect them and use that in an integrated platform. And that is very, very critical, I believe. And of course, what we are also proposing is a national test facility, so that you test drive these things before it's actually deployed. It's very hard to test drive new things, and there is no national facility. Well, there are pieces you can do right now, but you cannot do the whole building system at any place, and that's what that's when National Lab is very good at. This is sort of the center. Here you have the industrial consortium, UTC handles all this, but we're looking at many other industries. There's a fragment, we want to bring them together. And we're looking at Federal Department of Energy. We've had several meetings now with DOE, California Energy Commission, and Public Utility Commission of California. Very, very keen in this because it aligns with California goals as well. And there's some research, there's a user facility that people could, startup companies could go there and try out the latest sensor wireless network, for example. And of course, these are all the stakeholders, utilities, ASHRAE, architecture, engineering firms, building operators, ESCOs, they all have to be engaged in this, otherwise it'll never go to the marketplace. So that's the whole idea of Hyperbrake. I'll stop here with just saying that this is open development, we want to do it in the Linux way. There's some strategic value to bring National Lab, Industrial Consortium, as well as universities together. We really want to get some of those simplistic models of fluid mechanics as opposed to DNS into a building spice kind of things. Technology, of course, the National Test Facility, of course, we need a whole, as you heard, we need a whole new breed of students and scientists and engineers and architects who can talk to each other and understand the issues and their jobs, et cetera. So let me just stop here by saying this is, the demand side is a huge opportunity. I think is the lowest hanging fruit in this, and we're trying to look at the lowest of the lowest hanging fruit. So let me stop here, and thank you very much for your attention. Yeah.